If Stephen Hawking was right about black holes, then quantum mechanics, the most successful theory in the history of science, is completely broken. Your smartphone shouldn't work. Chemistry shouldn't exist. The entire digital age is built on a lie. That's what was at stake in 1993 when I stood up at a conference and told the most famous physicist alive that he was dead wrong about information. For 28 years, we battled over this question. Careers were made and lost. Friendships were tested. And in the end, Stephen admitted I was right. Let me take you back to 1974. Stephen Hawking, already famous for his work on black holes, made a stunning announcement. Black holes, he said, aren't completely black. They emit radiation, thermal radiation. They glow. And over trillions of years, they evaporate completely. Now, this was brilliant work, groundbreaking. It connected quantum mechanics to general relativity for the first time. But there was a problem, a catastrophic problem that Stephen himself pointed out. If a black hole evaporates completely and disappears, what happens to all the information that fell into it? Let me explain what I mean by information. I don't mean your emails or your text messages. I mean the fundamental quantum information that describes the exact state of every particle. In quantum mechanics, information is sacred. It's conserved. It never disappears. That's not just a preference, it's a fundamental law. If you know the quantum state of a system right now, you can in principle calculate what it was in the past and what it will be in the future. The evolution is deterministic. Information is never truly lost, but Hawking's calculation said drop a book into a black hole, wait long enough, and the black hole evaporates into thermal radiation, random, featureless heat. The information in that book, gone, destroyed, erased from the universe forever. Think of it like this. Imagine I take an encyclopedia and I burn it. The information isn't really destroyed. It's scrambled into smoke and ash and heat. But if you were clever enough and had perfect knowledge of every molecule, you could in principle reconstruct what was burned. Quantum mechanics says this is always true. Information can be scrambled but never destroyed. Hawking was saying black holes are different. They actually destroy information. It's not scrambled, it's gone. Now, Stephen knew this was radical. He knew he was threatening quantum mechanics itself, but his calculation was solid. The math was right there, and he concluded quantum mechanics must be modified. Information must be allowed to disappear in black holes. I heard about this in the early 1980s, and I remember thinking that can't be right. Something's wrong with that picture, but I didn't know what. Stephen was brilliant, sharper than almost anyone. If he said information is destroyed, you had to take it seriously. For years, most physicists just accepted it. They assumed Stephen had figured something out that the rest of us were missing. Black holes must be special. Maybe information can be destroyed. Maybe quantum mechanics needs revision. But I couldn't let it go. See, I come from the Bronx. My father was a plumber. He taught me. If something doesn't make sense, don't just accept it because someone famous said it. Figure it out for yourself. And this didn't make sense. If information can be destroyed in black holes, why not in other situations? Where do you draw the line? And if quantum mechanics is wrong about this, what else is it wrong about? The entire edifice of modern physics was built on quantum mechanics. You don't just throw that away because black holes are weird. The battle really began in 1993. I was at a conference in Santa Barbara, the Kavli Institute for Theoretical Physics. Stephen was there to give a talk defending his position. The room was packed. Everyone wanted to hear what Hawking had to say. He presented his argument. Black holes evaporate. The radiation carries no information. Information is lost. Quantum mechanics needs to be modified. Case closed. I sat there listening, and I felt this surge of, I don't know if it was anger or excitement or both. I knew he was wrong. I didn't have the complete answer yet, but I knew something was off in his reasoning. During the Q&A, I stood up. The room went quiet. You have to understand, this was Stipi Abi Ainge. You don't just contradict Stephen Hawking in front of 200 physicists. But I couldn't help myself. I said something like, Stephen, I think you're making an assumption that isn't justified. You're assuming that the information really goes inside the black hole and stays there. But what if it doesn't? What if it's preserved on the surface, the event horizon, and then released with the radiation? Stephen's response was polite but firm. He basically said, no, the calculation is clear. The information goes in and it doesn't come out. That was the opening shot. After that conference, Gerard Hooft, brilliant Dutch physicist, Nobel Prize winner, pulled me aside in the hallway. He said, Lenny, I think Stephen is wrong about this, but I don't know how to prove it. That conversation changed everything. Gerard and I started working together, not in the same room. We were at different universities, but we'd meet at conferences, exchange ideas, emails, phone calls. Gerard had this radical idea, holography. He was thinking about the boundary of space-time regions, about how information might be encoded on surfaces rather than in volumes. I thought he was onto something huge. Over the next few years, I developed what I called black hole complementarity. The idea was this: there's no single description of what happens when something falls into a black hole. The observer who falls in sees one thing, they pass smoothly through the event horizon and fall toward the singularity. The observer outside sees something completely different. They see the information smeared out on the horizon, never going inside. Both descriptions are valid. Neither observer can verify the other's view. It's like complementarity in quantum mechanics, wave or particle. Depending on how you measure, black hole complementarity says inside or outside, depending on where you observe from. I wrote this up in a paper with my colleagues Russ Thorlacius and John Uglum in 1993. We called it black hole complementarity and the Hawking evaporation process. That was my first major counterattack. Stephen wasn't convinced. He wrote papers arguing against complementarity. I wrote papers defending it. Other physicists jumped in, some on my side, some on his. Don Maralf, John Preskill, Kip Thorne, Gerard, everyone had an opinion. Look, I have to be honest with you. In those early years, I wasn't 100% sure I was right. Stephen's argument was powerful. His math was solid. I had intuition and a conceptual framework. But I didn't have a complete airtight proof. There were nights I lay awake thinking, what if he's right and I'm just being stubborn? But I kept pushing, because the alternative, that information is really destroyed, would have been the end of physics as we know it. In 1997, I had another breakthrough, working with Tom Banks, Willy Fischler, and Steve Schenker on something called the BFSS matrix model, a completely different project about M theory. I started seeing connections. Information in quantum gravity isn't localized the way we think. It's distributed, holographic. That same year, Juan Maldacena, brilliant young physicist at Princeton, discovered the ADS-CFT correspondence. This was huge. It was a concrete realization of holography. A quantum field theory on the boundary of a spacetime exactly describes the gravity in the bulk. Information on the surface equals information in the volume. Juan's work didn't directly solve the black hole information paradox, but it gave us a tool. A way to think about quantum gravity that preserved information by construction. I called Stephen after Juan's paper came out. I said, Stephen, this changes everything. Holography is real. Information can't be destroyed. His response, maybe in ADS space, Lenny, but not in realistic black holes. The war continued. The breakthrough that really turned the tide came from thinking about something called black hole entropy. Jacob Bekenstein had figured out in the 1970s that black holes have entropy, a measure of disorder, of missing information. And Hawking had calculated exactly how much the entropy is proportional to the surface area of the event horizon, not the volume. That's weird. Think about it. If I have a box, the amount of stuff I can put inside is proportional to the volume, right? Not for black holes. The amount of information a black hole can hold is proportional to its surface area. It's like saying everything inside a room is actually painted on the walls. That's when it hit me. In 1994, I wrote a paper called The World as a Hologram. I was building on Gerard's ideas, taking them further. The claim was radical. The three-dimensional world we experience might actually be a projection from information stored on a two-dimensional surface. Like a hologram, a flat film that creates a 3D image. For black holes, this means the information that falls and doesn't really geo-inside. It's encoded on the event horizon, the surface. And when the black hole evaporates via Hawking radiation, that information can escape. It's scrambled, incredibly hard to read, but it's not destroyed. Here's the analogy I love. Imagine you drop a book into a fire. The book burns, turns to smoke and ash and heat. If you're clever enough, if you know the exact quantum state of every molecule of smoke and ash, you could in principle reconstruct the book. It's scrambled, but the information is there. Black holes are the same. Drop a book into a black hole. The black hole eventually evaporates into Hawking radiation. The information is scrambled, probably more scrambled than anything else in nature. But it's there. You just need to be smart enough to decode it. Now, Stephen had an objection to this. He said Hawking radiation is thermal. It's random. There's no way the information is hidden in there. It's like saying you can reconstruct a book from the random heat emitted by a fire. Impossible. And I said, no, it locates thermal if you only measure part of it. But if you collect ALL, the radiation, over the entire lifetime of the black hole, and you do an incredibly complex quantum computation, the information is recoverable. Patrick Hayden and John Preskill later proved this mathematically. You need to wait until the black hole is half evaporated, then do an exponentially hard computation. But it's possible in principle. Here's what I think half the community still gets wrong about this. They want a simple, local explanation of how information escapes. They want to point to a specific Hawking photon and say, there's the information from that book. But that's not how quantum mechanics works. The information is encoded non-locally. It's in subtle correlations between AL, the radiation. It's holographic. You can't see it if you're looking at pieces. You have to see the whole picture. The holographic principle became my weapon. Every paper I wrote after 1994 was building on that foundation. Information lives on surfaces. Space is emergent. What looks three-dimensional is actually a projection from something lower dimensional. And slowly, very slowly, the tide started to turn. The endgame came in 2004. 28 years after Hawking first proposed information loss, I was 64 years old. Stephen was 62. There was a major general relativity conference in Dublin, GR17. Stephen was scheduled to give a talk. And word started spreading before the conference he's going to announce something big. I flew to Dublin not knowing what to expect. Part of me thought, is he going to double down? Present an even stronger argument for information loss. Stephen's talk was scheduled for the final day. The room was absolutely packed, standing room only. Everyone in the gravity community was there. Stephen wheeled to the front of the room. His computer-generated voice filled the space. And then he said it, I have been thinking about the black hole information paradox for over 30 years, and I have changed my mind. Information is not lost. The room erupted. People were talking over each other. I sat there stunned. Gerard was next to me, grinning. Someone behind me slapped my shoulder. Stephen explained that he'd been working through the details of holography using Juan Maldaceno's ADS-CFT correspondence, and he now believed information is preserved after all. Encoded on the horizon, released with the radiation, exactly as Gerard and I had been arguing. He didn't use the word wrong. He didn't say Susskind was right. That's not how scientific talks work, but everyone in that room knew what had just happened. After the talk, I went up to Stephen. We shook hands. Well, I shook his hand. He couldn't move as easily. I said something like, Stephen, I'm glad we finally agree on this. He smiled, that mischievous smile he had, and his computer said, it was a good argument, Lenny. That was it. 28 years. Over. Now here's the thing. This wasn't a defeat for Stephen. It was physics working the way it's supposed to work. You propose an idea, you test it, you argue about it, and eventually the truth emerges. Stephen was brave enough to follow the evidence wherever it led, even if it meant admitting he'd been wrong for 3 decades. A lot of scientists can't do that. Their egos get in the way. Stephen's ego was legendary. He was famously stubborn. But ultimately, he cared more about the truth than about being right. That's what made him great. And honestly, the war made both of us better physicists. I wouldn't have developed black hole complementarity without Stephen's challenge. I wouldn't have been forced to think so deeply about holography. The fight sharpened my thinking. Stephen passed away in 2018. I think about him often. We were opponents for 28 years, but I considered him a friend. Physics is better because he was willing to be wrong. So what did we learn from this 28-year war? What came out of it besides settling one argument? First, the holographic principle. This wasn't just about black holes. It's about the fundamental nature of reality. The idea that information is stored on surfaces, that three-dimensional space might be emergent from lower dimensional physics. This has become one of the central ideas in theoretical physics. Juan Maldaceno's ADS-CFT correspondence is built on it. String theory relies on it. Quantum gravity research for the past 25 years has been shaped by holography. Second, black hole thermodynamics. We now know that black holes behave like thermodynamic systems. They have temperature, Hawking's great discovery. They have entropy, Bekenstein's insight. They obey laws analogous to the laws of thermodynamics. This connection between gravity and thermodynamics is deep. We're still figuring out what it means. Third, quantum information theory became part of mainstream physics. Before this debate, most physicists thought quantum information was a niche topic for computer scientists. Now we understand it's central to understanding quantum gravity. Black holes are information processors. They scramble information at the fastest possible rate. I proved this with my student Yasuhiro Sakino in 2008. Fast scramblers, the universe's ultimate computers. Fourth, we learned that quantum mechanics and general relativity aren't separate theories that need to be unified. They're already unified, we just didn't see it. Entanglement creates geometry. This is the ER-EPR idea I developed with Juan Maldaceno in 2013. Wormholes and quantum entanglement are the same thing. Geometry asks quantum mechanics. And fifth, and this might be the most important, we learned that physics isn't done. The information paradox is technically solved, but we don't understand how the information gets out. The mechanism is still mysterious. My current work on quantum complexity is trying to crack that. How does a black hole encode information? How does it release it? What's the actual process? I think the answer lies in understanding complexity. Not just entropy, that's about how much information there is. Complexity is about how hard it is to decode. Black holes maximize complexity. They're the hardest systems in nature to decode. And I think understanding that, really deeply understanding it, will be the key to quantum gravity. This connects to everything. De Sitter space, the expanding universe we actually live in, probably has similar information structure to black holes. The anthropic landscape of string theory, the 10,500 possible universes I proposed in 2003 might be related to the computational complexity of finding the right vacuum. It's all connected. After 50 years of doing physics, I'm more excited now than I was at 30, because we're finally asking the right questions. You know what the best part about physics is? It doesn't care about egos. It doesn't care how famous you are or how many prizes you've won. The universe has laws, and they don't bend for anyone. Not even Stephen Hawking. I'm 86 years old now. I've been doing physics for over 50 years. I've seen theories rise and fall. I've seen brilliant ideas turn out to be wrong. I've been wrong more times than I can count. But here's what I've learned: being wrong is part of the process. Stephen was wrong about black hole information for 28 years. That doesn't diminish his legacy one bit. In fact, his willingness to change his mind in 2004, to admit he'd been wrong, that might be his greatest achievement. The information paradox taught us that the universe is stranger than we imagined. Three-dimensional space might be a hologram. Time might emerge from quantum entanglement. Black holes might be the fastest computers in nature. And we're just getting started. There are still problems I want to solve before I'm done. De Sitter holography. Understanding the quantum structure of our expanding universe. That's my current obsession. I don't know if I'll crack it, but I'm going to try. Because that's what physicists do. We ask questions about reality, we argue about the answers, and we keep pushing until the universe tells us its secrets. And sometimes, on a good day, it does.